Okay, everyone, let's have a look at some of these questions then that you're asking about. Uh, so we will start with the relatively easier ones, and we would want to do all of them today. And looking at the number of questions that I see in the chat box, I'm not sure if we would be able to start the next topic, but let's do these questions first then. Okay, so I have already seen 74 and 44 in the last class. So I think 74 was the relatively easier one. Let me have a look at the other ones quickly as well. So we can do them in order of increasing difficulty. Okay, so we have question number 13 and 29. Okay, so this is 29. Okay, and we have 13. Okay, let's start with these questions then. I'm going to start with 74. Let's start with that. This is the shortest of them all, I think. Let's start with this one. Okay, question number 74 from the worksheet. It says A and B are 2 points which are 10 meters apart on the same horizontal plane. A particle P starts to move from rest at A directly towards B with constant acceleration. So we are given that the acceleration is constant. They are 10 meters apart, the two particles. Another particle Q is moving directly towards A with constant speed 0.75 meter per second and passes through B at the instant that P starts to move. At time t seconds after this instant, particles P and Q collide. Find the value of T. Okay, now let's think about this. Since we don't have a diagram given, it's going to make things simpler to understand if we draw a rough sketch to understand the situation better. So we have this horizontal plane, and on this plane we have 2 points. So there's one point A here, there's another point B here. The distance between points A and B is 10 meters. P starts from rest at A and it goes towards B. So there's a particle P that's going from this point to the right side, and its initial velocity is 0 meters per second. It starts from rest. And its acceleration is constant at 0.5 meters per second square. There's another particle Q that's moving directly towards A with constant speed 0.75 and passes through B at the instant that P starts to move. Now, particle Q is moving at constant speed. Okay. And it passes through this point B at the instant that P starts to move. So when P starts to move from A to B, Q is crossing the point B. So Q is here at that point, at that instant. And what's the speed of Q at this point? It's 0.75. And this speed is constant. It's not changing. It's 0.75 meters per second throughout. At time t seconds after this instant, particles P and Q collide. So there's some point between P and Q, between A and B, where the particles collide with each other. Now, we don't know where exactly that point is going to be. Let's assume that is maybe somewhere here. Now, we don't know exactly where that is. So I'm just going to mark a point randomly. Do not assume it to be the midpoint. Okay. Don't make that assumption. Let's say this is point X, where the collision happens. Now, this is the point where the collision happens. That means P has moved from A to this point, and Q has moved from B to this point as well. And they have both taken t seconds to reach this point, the point of collision. We need to find the time taken until this collision happens. Now, let's try to understand what information we have given about both the particles. So we have particle P and we have particle Q. Now, particle P is moving towards the right. So we should take the right direction as positive for particle P. Q is moving towards left. We can take left positive for particle Q. Okay. Now, what do we know about P? For P, we know the initial velocity is 0. We know acceleration. Acceleration was given to be 0.5. These are two pieces of information that we have about A. What do we know about P? Sorry, what do we know about Q now? Q is moving towards left. Its initial velocity was 0.75. But if you think about it, this particle is actually moving at constant velocity. Its velocity is not changing. So this is one case where you could actually use that speed equals distance over time formula as well. If you wanted distance equals speed into time, you could do that. But if you were to use constant acceleration formulas, you could also use those formulas here, because if the velocity is constant, what that means is the initial velocity is going to be 0.75 and the final velocity is also going to be the same. And since there's no change in velocity, acceleration is zero. All right, so that's the information that we have about Q. We need to find the value of T. What other information do we have now? We do not know final velocity or time taken or displacement for particle P. So now we need to see what variables are common between the two objects. What's common between P and Q? P and Q, they are both passing A and B at the same time instant, respectively, right? So when A starts from P, that is when Q passes B. Sorry, the other way around. When P starts from A, that's the same time instant when Q passes B. And they're both reaching X at the same point as well. What that means is the time taken for P to reach X is going to be the same as the time taken for Q to reach X. So if we were to say the time taken by particle P is T, the time taken by particle Q would also be T. Their time takens are common. So that's what we do. We take their time variables because they're common between the two. We would not be introducing too many variables in this case because this is common between the two. Okay. Now, what else? We also know that the total distance between A and B was 10 meters. So that means whatever is the displacement covered by P and whatever is the displacement covered by Q, their sum has to be equal to 10. That is an equation that we can use here to connect their displacements. We can say displacement of P plus the displacement of Q, that should equal 10. And now we can see how we can find displacement using the information that we have. So for Q, we know everything else. For P, we only know these three things, U, A, T, and S. Which equation connects these four things? We can use this equation, S equals UT plus half AT squared, to find the displacement of P and also to find the displacement of Q. What's the displacement of P? P's displacement would be UT, that means 0 times T, plus half into A, which is 0.5 into T squared, plus displacement of Q, which is U, which is 0.75, multiplied by T, plus half into A, which is 0 into T squared. And this equals 10. All right. Let's simplify this. 0.5 over 2, that's 0.25 T squared, plus 0.75 T. This gets cancelled. This equals 10. Is that okay? Is that what we get? Yeah. Now we can simplify this. This gives us we can take everything to the left side for now. 0.25 T squared plus 0.75 T minus 10 equals 0. How do we get rid of decimals? 0.25 is 1 over 4. If we actually multiply this whole equation by 4, we can get rid of the decimals. You don't necessarily have to do it. You can use quadratic formula directly at this point and then write down the answers. That's perfectly okay. But if you were to simplify this equation and remove the decimals, you could multiply the whole equation by 4. What would that give you? T squared, 0.75 into 4, that's going to be 3. So 3T minus 40 equals 0. Now you can see if you can factorize this. 40, you can use 8 and 5. T squared plus 8T minus 5T minus 40 equals 0. You get two factors from this, T plus 8 and T minus 5, which means T either equals minus 8 or T equals 5. Time cannot be negative. That means the value of capital T that you're looking for, that's 5. So the collision happens when time equals 5. That is what we were looking for. Make sense? That's the first part. Okay. Now the second part says find the speed of P immediately before the collision. So basically, what's the final speed of P at the point X for this? What is the speed of P? That's the second part. That's pretty straightforward. You can just use this formula. V equals U plus A times T. Initial velocity of P was 0. Acceleration was 0.5. Right? And time taken is 5. And that's going to give you 2.5 meters per second. Is that all right, Naima? Make sense? Okay. All right. So that was a relatively simpler one, I think. Maybe you were just doing some plus minus errors, taking positive negative directions. The rest of it was not that complicated. Okay, let's have a look at the next one. Okay, let's do 13 or 29, one of them. So we'll do 44 at the end, right? That's, I think, the most complicated of them all, or at least looks like that. Yeah, we'll do this towards the end. Let's do 13 or 29 first. 29 is this one. Okay, let's start with this. Question number 29. Okay, so it says a particle P travels in a straight line. It passes through the point O of the line with velocity 5 meters per second at time t equals 0. So there's some point O here. At this point O, we are given that the velocity of this particle is 5 meters per second. Time is 0 at this point. P's velocity after leaving O is given by this. This is an equation that we have for P's velocity after leaving O. Now we don't know which direction it's moving, and let's assume it's horizontal and it's moving like this. It's moving in a straight line, right? So straight line could be anywhere. Let's say it's like this. The particle is moving in this direction. This is the direction of the particle. P is going towards right side like this. Its velocity is given by this function. Let me write that down. V equals 0.002 t cube minus 0.12 t squared plus 1.8 t plus 5. That is the velocity function. Okay. Now it says velocity of P is increasing when time is between 0 and t1 and when time is greater than t2, and the velocity of P is decreasing when time is between t1 and t2. Now, that's a lot of notations that they've used here, but all that means is we are basically dividing our journey into different parts like this. That the first part is maybe 0 to t1, and then t1 to t2, and then t2 onward. Right? So there are different parts of the journey. From 0 to t1, the velocity is increasing. Right? That's what they're saying. So velocity is increasing between these 2 points. Then from t1 to t2, in this part, you see the velocity is decreasing in the middle part. And it's also increasing after t2. So it's increasing on the right side as well. So increasing here, and decreasing in the middle. Right? That's what is happening. It's first increasing and then decreasing and then increasing again. We need to find the values of t1 and t2 and the distance OP when t equals t2. All right, now how do we understand this? Let's think about this. Now notice it's a cubic function, right? It's a cubic function. And what they're saying is the velocity is increasing first, and then it's decreasing, and then it's increasing. So it's going to look like this. It's something like this, right? It's increasing, and then it's decreasing, and then it's increasing again, right? That is what is happening. The velocity increases, then decreases, and then increases again. Now, from time equals 0 to time equals t1, the velocity is increasing. And then from t1 onward, it starts decreasing. What that means is this point here, this should be t1, right? Because the velocity was increasing earlier and then it started decreasing. So this is the point where the velocity would be maximum, right? And then it starts decreasing. From t1 to t2, the velocity decreases. And then at t2, it starts increasing again. So that means this point here should be t2. So t1 and t2 are basically the turning points of this function. So all you have to do is find the turning points of this function. Make sense? Velocities, so you can also think of it like this. In mechanics terms, you can also think of it like this, that when the velocity is increasing, acceleration is positive, right? It's a positive value. Acceleration is positive here and acceleration is positive here. And when acceleration is decreasing, and when velocity is decreasing, acceleration is negative, right? So acceleration was positive, then it becomes negative, then it becomes positive again. Now between positive and negative, acceleration is going to be 0 at some point. So at t1, acceleration is going to be 0. And at t2 as well, acceleration is going to be 0. These are 2 points when acceleration is 0. How do you find acceleration? Acceleration is the derivative of velocity. So you could say dv over dt. That's also acceleration. So you could think of it either way. You could either say you would find acceleration function and put that equal to 0, put the acceleration equal to 0, that will give you the value of time. Or you could think of it using differentiation concepts, that this is what the graph looks like. It's a curve like this. And you are basically looking for the turning points of that graph, right? So you're looking for T1 and T2. These are the turning points of this graph. How do you find turning points? Find the derivative, put the derivative equal to 0, put the gradient equal to 0, and that gives you the turning points. Is this point clear to everyone? Any confusion on this? All right. So now all you have to do is find this derivative. Find this derivative, put that derivative equal to 0, and see what that turns out to be. 0.002. Why did it take a equal to 0? That's what I'm saying. So let me write that down on the side. 0 to t1, and then t1 to t2, and then onward. Between 0 and t1, what is happening to acceleration? In this region, acceleration is positive. And then in this region, acceleration is negative because velocity is decreasing. And then in the last region, acceleration is positive. Now, as you go from positive to negative, at t1, at this cutoff point, what happens? Acceleration is going to be 0, right? So when you go from a positive value to a negative value, 0 is what comes in the middle, right? And similarly here, when the acceleration goes from negative to positive again, here again, acceleration is going to be 0. So when it goes from positive to negative or from negative to positive, in the middle, there's going to be 0. Or you could think of it graphically as well. So if you don't want to think about acceleration, you could also think of it this way, that this is what the velocity function looks like, right? This is the velocity function. You just want to find the turning points of this velocity function. How do you find turning points? You find the derivative, that's dv over dt, and put that derivative equal to 0, right? That's all that you have to do. So you could think of it either way. Now, how do you differentiate it? 0.002 into 3, that's going to be 0.006 t squared, minus 0.12 into 2, that's 0.24 times t, plus 1.8, that's the derivative. Now what we do is you put dv over dt, or acceleration, however you want to think of that, you put this equal to 0. Why? Because you're looking for the turning points. Okay, now put the derivative equal to 0. That gives you this quadratic equation. Now, how do you solve this quadratic equation? Now, you could convert it to integers first by multiplying it by 1,000 maybe, but it's simpler to just put values in the quadratic formula and use your calculator to find the result. So just write this one single step. T equals minus b, that's minus into minus 0.24 plus minus square root of minus 0.24 whole squared minus 4 into a, which is 0.006 into 1.8 whole divided by, whole divided by 2 times a, that means 2 times 0.006. That's going to give you the values of t. I'm going to put this whole thing in my calculator directly in the equation function. Now, this step is important. Then you can write down the answers. So it's a polynomial equation, degree 2, 0.006 minus 0.24 and 1.8. So one value that I'm getting is 30, and the other value that I'm getting from my calculator is 10. All right. Now, T1 is supposed to be the smaller value. T2 is going to be the bigger value. The time, right? Time is on the horizontal axis. Remember, this is the time axis, the horizontal axis. So we say this is T1. T1 equals 10. This is T2. That is 30. That is what we were looking for in the first part. That's one thing that we were looking for in the first part. All right. Now it says find the distance OP when t is equal to t2 at time 30. We want to find the distance OP. O is the starting point. That means when time equals 0. P is the particle. Where is the particle when time equals t2? That's what you need to find out. Now, are they talking about distance traveled or displacement here? What does this mean? Distance OP. Is it distance traveled or displacement? Do we need to check for the change in direction? Would we need to do that? What does distance OP means? Distance OP is the same thing as displacement. Remember, we talked about this terminology in the very first few sessions on kinematics. Yeah, so if you have this, if they say distance AC, that's the distance between 2 points. So this is A, this is C. Even if the particle was going like this, going from A to B and then B to C, distance AC means it's the distance between 2 points A and C. And that's just 30, which is the same as displacement. So distance that they're asking for here, distance OP, that's not the distance traveled by the particle from O to B. That's the distance between 2 points O and B. And that's the same as displacement. For distance traveled, we have to check for change in direction. We talked about this the other day as well. When we have to find distance traveled, we always put v equal to 0 to check for change in direction whenever we're looking for distance traveled. But we're not looking for distance traveled here. We are looking for distance between 2 points, and that's the same thing as displacement. So all we have to do is, we have the velocity function. This is what the velocity function looks like. We need to find the displacement of the particle from time equals 0 to time equals 10. That is all that we've got to do. Find time equals 0, time equals 30, sorry, because the value of T2 is 30. They want the displacement, the distance OP when T equals T2, T2 value is 30. So that's what we're looking for. We just integrate this function, input limits in that, and that's 0.002 T raised to power 4 divided by 4 minus 0.12 cube divided by 3 plus 1.8 T squared over 2 plus 5 times T. You can just input the limits because you're looking for the value of displacement from time equals 0 to time equals 30. And that's going to give you the result. Let's simplify this function first of all. 0.002 divided by 4. That is 0.0005 T raised to power 4 minus 0.04 T cube plus 0.9 T squared plus 5 times T. Input T equals to 30 in this one, and then put T equals 0. Subtract the two cases, so you have 0.005 into 30 raised to power 4 minus 0.04 into 30 cube plus 0.9 into 30 squared plus 5 into 30. Subtract from this the case when you input t equal to 0. In this case, since you have t in every single term, multiplying with every single term, when you input t equals 0, everything is going to become 0 basically. So you just write 0 there. Now just evaluate this and see what that gives you. 0.0. Can somebody do this calculation for me just to confirm? I'll do this on my end as well. So I'm getting 0.04 into 30 cube plus 0.9 into 30 squared plus 5 into 30. Okay, 285. Is that correct? Can somebody confirm this?
Yes, sir.
Okay, so that's the displacement that we get. This is the distance OP that they were asking for. Distance OP. That is 285 meters. Okay. That's the first part of this question. Let's look at the second part quickly now. Second part says find the velocity of p when time equals t2 and sketch the velocity time graph for the motion of p. Okay, now velocity of p when time equals t2. We have the velocity function given. This is the velocity function. All you have to do is put time equals 30 here, and that will give you the velocity at this particular time. You can see what that turns out to be. 0.002 into 30 cube minus 0.12 into 30 squared plus 1.8 into 30 plus 5. And that's giving me 5 meters per second. So at time t equals 30, I'm getting 5 meters per second, right? Now they ask us to find, to draw the velocity time graph of this function. Let's see how the velocity time graph is going to look like. This is time, this is velocity. Let's draw this graph. So what are the important points in this journey now? One point is 0, right? That's when the particle is starting. And then we had two turning points of that graph, T1 and T2. One is 10, and then you have 30. Let's mark those 2 points here. Let's say we have 30 somewhere here. Then we have 2 points in the middle here somewhere, one here and maybe one here. This is 10, this is 30, sorry, 20. Okay, so we know the velocity when time equals 0. What's that? When time equals 0, what's the value of velocity? It's 5. So it's starting from 5 meters per second. Let's mark 5 somewhere. Let's say this is 5. So it's starting from this point. And we also have the velocity when time equals 30 now. That is also 5. This value is also 5. We need to sketch this velocity time graph now. All right. How do we draw this? it's a cubic function. The shape is going to look something like this, right? This is roughly what the shape of the graph is going to be. But now we also need the value of velocity when time equals 10. We also need this point here. I don't think we have calculated that anywhere before. Yeah, we haven't. Let's find that as well now. So we also try inputting t equals 10 to find the corresponding velocity at that point. What happens when t equals 10? When t equals 10, the velocity is 13. So at time 10, the velocity value is 13. So if this is 5, we can say 13 is maybe somewhere around here. No, it's maybe going to be here. So at time equals 10, we have this point here. So what is the graph going to look like? It's going to be like this. It goes here. And then the second turning point is on the other side there. This is the first turning point. And the graph goes like this. And it goes like this. This is standard like this. We don't know what's happening afterwards. Just make a curve like that. This is T1. This is one important point. This is T2, the other turning point, the other important point. You have the velocities corresponding to them, 5 and 13. And that's what the velocity time graph looks like. Is that okay? Any problem with this?
No, sir.
No? Okay, so that's part 2. Let's move on to the next one now. The next question is question number 13 from the worksheet. Okay, let's start this quickly. Question number 13. Okay, so it says a train travels from A to B, a distance of 20,000 meters, taking 1,000 seconds. A to B, 20,000 meters, 1,000 seconds. It has 3 stages. The first stage, the train starts from rest at A and accelerates uniformly. That means it's constant acceleration until its speed is v meters per second. In the second stage, the train travels at a constant speed v for 600 seconds. And during the third stage, the train decelerates uniformly. Again, that's uniform deceleration, coming to rest at B. Sketch the velocity time graph for the train's journey. Now, let's sketch this graph. Time cannot be negative, so we can only consider the positive part. For time, at least, velocity might be negative, so we can extend it downwards if it turns out to be negative at some point. But for now, let's just consider this. So it's starting from rest. Starting from rest. In total, it's taking 1,000 seconds. So the total time taken is 1,000. So this point is 1,000 seconds. In the first stage, it starts from rest. So initial velocity is A. It accelerates uniformly until its speed is v meters per second. Now, we do not know how much time it takes, right? So we don't have any idea about that. Let's just mark any point here. Let's say this point is T. It accelerates uniformly. That means constant acceleration, and acceleration is constant. That means the gradient of this graph is supposed to be constant. That means it's a straight line. So we can mark some point V here on the vertical axis. That's the speed that it reaches at this point T. What is the graph going to look like? It's a straight line from origin to this point. And that's the first part of the graph. Then the speed is constant for 600 seconds. So now we have a straight line after this for 600 seconds. Let's say it looks like this. Again, we don't know what the end point is going to be. If this is T, we could say this is t plus 600, right? And then it decelerates uniformly in the third stage and comes to rest at a point B. So it decelerates uniformly. That means constant deceleration. It's a straight line like this again, right? That's what the graph looks like. That's all that you have to show in your sketch. It's not necessary for you to mark these points either, right? T and T plus 600, it's not necessary. 1000 is necessary. And then just the shape of it's just the shape of the graph that matters, that it should be a straight line like this. This point should be V here, then it should become constant, and then come back like this. That's the first part of the graph. First part in which we have to draw the graph. Now in the second part, it says find the value of V. Okay, now V is this point, right? That's what you need to find out. What's the information that's given in the question? It says that the distance traveled is 20,000 meters, and the end result here is 1,000. It's a velocity time graph. How do you find displacement from a velocity time graph? It's the area under the graph. The object, the train is only moving in one direction, right? Because the velocity is positive throughout. It's not changing direction. That means displacement is going to be the same as distance in this question, right? So you can just find the area under the graph and put that equal to 20,000, and that should give you the value of V. Okay, let's try that. How do you find the area of this graph? This is a trapezium. Area of this trapezium, what should that equal? This area. This should equal 20,000 because we're given that the total distance traveled is 20,000. We put this equal to 20,000. Now, how do you find area of trapezium? That's half into sum of parallel sides into height. What are parallel sides? One side is this, that's 1,000, and the other side is this. This is 600, right? So 1/2 into sum of parallel sides, 1,000 plus 600 multiplied by height. Height is V. That equals 20,000. And that should give you the value of V. That's 20,000 multiplied by 2 divided by 1,600. And that's giving me 25 meters per second. That's the value of V that we were looking for. Okay, that's the second part. Okay. Let's look at the third part now. Given that the acceleration of the train during the first stage of the journey is 0.15, find the distance traveled by the train during the third stage of the journey. Okay, so now we know that in the initial stage, in the initial part of the journey, so we also know this is 25 now, this is 25. And we are given that this acceleration is what? 0.15. How do you find acceleration of this graph? Acceleration of this graph is basically the gradient of this graph. So that means the gradient of the first part of the journey is 0.15. We can find the value of t using that. How do you do that? You can say this is, this point is t and 25 now, right? The horizontal coordinate is t and the vertical is 25. What's the gradient of this line? That is 0.15. So you can say acceleration equals 0.15. That means the gradient equals 0.15. What's the gradient? 25 minus 0 divided by t minus 0. That should equal 0.15, and that should give you the value of t. 0.15 t equals 25, and t turns out to be 25 over 0.15. That's giving me 500 over 3. Or in decimals, that's 166.67. Okay, so now we know the value of t here. This is 500 over 3. Now, if this is 500 over 3, what about this point? You just add 600 to that. So 500 over 3, this is therefore going to be 2,300 over 3, which in decimals can be written as 766.67. So now we know this point as well. We want to find the distance traveled by the train during the third stage of the journey. What's the third stage of the journey? This is the third stage of the journey. We just need to find this area, right? Now we can find this area. It's a triangle. How do you find area of this triangle? You know the height of the triangle, that's 25. You know the base now as well. What's the base? 1000 minus 766.67. You can find that area. Area of distance traveled during the third part of the journey. Half into base, which is 1000 minus 766.67 into height, which is 25. And that's going to give you that area, right? 1 over 2 into 1000 minus 766.67 multiplied by 25. And that's giving me 2916.6 meters. That's the distance traveled during the third stage of the journey. Is that okay? Make sense? Marina, is that okay? You understand this? Okay, great. Let's look at the last question now for today. And then in the next class, we will start our next topic, which is Newton's second law of motion. Now, those of you who have done physics, I'll just tell you what you have in the next topic. So maybe you can start attempting some questions already. Basically, Newton's second law of motion just have that formula F equals ma, right? That's all that you have. Everything else remains the same. Forces, you've done the forces concepts in the first topic. You've done kinematics topics in the second topic. In the third topic, we will just be connecting forces and kinematics using this formula F equals ma. That's all that you will be using there. Okay, that's the only concept that you have in the next topic. So if you know this concept already from physics, maybe you can start doing practice questions. We will cover this in the next class, but just so you have time to practice more questions, you can start them right now as well. If you know this concept already, and do the rest of the questions from the friction worksheet and the kinematics worksheet. I'll upload the assigned questions as well. We will not have a new worksheet for that. It's the same two worksheets, friction worksheet and kinematics worksheet. You have questions related to Newton's second law of motion in these two worksheets as well. I'll be assigning those questions. Those of you who know this concept already, you can start working on those questions. We will be doing this concept in the next class now. Okay, just remember, if you have multiple objects, sometimes you'll have one object connected to another object. You apply this individually to each of those objects, right? Now, if you understand that, that's great. Try those questions. Otherwise, we will be doing that topic in the next class anyway, inshallah. Okay, so now let's have a look at question number 44. Then we end with that for today. Question number 44 from the worksheet. Now, this is a relatively lengthy one. Let me copy this. Okay, let's try this. So it says the diagram shows, is it all the same question? What's part A? Yeah, okay, all right. So you have 1A, 1B, and then 2A, 2B, 2C. Okay, that's what it looks like. Okay, let's have a look at this now. So it says the tractor travels in a straight line from a point A to a point B. The velocity of the tractor is v meters per second at time t seconds after leaving A. We have this velocity time graph given. The diagram shows an approximate. Okay, so it's an approximate velocity time graph. So it's not an exact graph, it's an approximate graph. All right. The graph consists of two straight line segments. One is the straight line, the other is this. Find the distance AB. Use the graph to find an approximation for distance AB. Now, of course, if the graph is approximate, if the graph is approximate, the distance that you find, that's also going to be approximate, right? Let's find this distance, AB. Okay, so total distance, how do you find that total distance? Part 1A. You just have to find this complete area, right? So just to save time, Jazib, can you tell me which part you're having a problem in? Because this first part is pretty straightforward. You just have to find this
Sir,
area.
the B
Yeah.
part of the second one.
B part of the second one. Okay, so we'll jump to that directly by I'll just give you hints about the previous part. Distance AB. That means you have to find the area of this triangle. Add to that the area of this rectangle. Right? Find the area of the triangle. Add to that the area of the rectangle at the bottom. That will give you the total distance traveled AB. Okay, because that's the total area under the graph. You can do that. What's the answer to the first part?
Sir, 4,000 meters.
4,000 meters. So assuming that you've done the first part, let's move on to the next one, part B. Find the acceleration of the tractor for time between 0 to 400 and for time between 400 to 800. Now, it's a velocity time graph. Acceleration is the gradient of this graph. So gradient of this part, that's going to be the acceleration in the first part, and then gradient of this part, that's going to be acceleration of the second part. Okay, so I think the gradients are the same in terms of magnitude. One is going to be positive, the other is going to be negative. You can find those gradients. Can you tell me the values of acceleration in the
So
first part?
0.02
Yeah,
and then the minus 0.02.
yeah, 0.02 and minus 0.02, right? So it's just the gradients of the two graphs, 0.02 and minus 0.02. Okay, then you have part two here. The actual velocity of the tractor. So this graph is basically giving you approximate velocity time graph. Now it says the actual velocity of the tractor is given by this formula for time between 0 and 800. Now these were straight lines. Now they have given us a quadratic formula. That means the actual velocity function is supposed to be a curve and not straight lines. All right, that's what they're saying. Find the values of t for which the actual acceleration of the tractor is given correctly by the approximate velocity time graph in part 1. Okay. Values of t for which the actual acceleration is given correctly by the approximate velocity time graph. Now, what are the acceleration values that you're getting from the approximate graph? One is 0.02 and the other is minus 0.02. They're basically asking you to find those time instances, those values of t at which the acceleration is actually equal to 0.02 or minus 0.02. Now, how do you do that? You have the velocity function given. The velocity function is 0.04 times t minus 0.00005 t squared. You can find acceleration function by just differentiating it. A equals 0.04 minus 0.0001 times t. That's the acceleration function. Now, all you have to do is put a equal to 0.02 first to see when the acceleration is actually equal to 0.02. That will give you one time value. Now you have to show working for this. Okay, so you'll say 0.02 equals 0.04 minus 0.001 times t. And then you say, let's input a equals minus 0.02. And that will give you minus 0.02 equal to 0.04 minus 0.001 times t. What's the value of t that we're getting from both of them?
Sir, 200 and 600.
So the first one is 200. Is the first one 200?
So
Yeah,
the first
the
one
first one,
is, yes.
yeah, first one should be 200 and the second one should be 600. These are the two values of t that we're getting. At these time instances, the value of acceleration is actually equal to 0.02 and minus 0.02. Okay, that's part 2a. Now, why is that? Basically, it will be something like this. It's a velocity graph. The intercept is 0. So the actual graph basically looks like this. What's the turning point? 200 and 600. If we were to find the turning point of this, 0.04 divided by 0.00005, that's 800. Yeah, turning point is going to be in the middle. The graph is actually going to look like this. The actual graph would be something like this, right? A quadratic function like this. So basically what we have done is there's some point 200 here and there's some point 600 here. These are 2 points at which the gradient of the actual graph is the same as the gradient of this approximate graph, right? So at these points, the accelerations from the actual graph and from these approximate graphs, they are the same, right? That's what we have calculated in this part, right? If you were to try to understand what represents, this is what it is actually. Okay, now that's the part 2a and 2b. We have to just leave this graph here in case we need that later. It says for the interval from 0 to 400 seconds, the approximate velocity of the tractor in part 1 is denoted by v1 meters per second. Express v1 in terms of t and show that v1 minus v is equal to this. Now, for the first 400 seconds, they're saying the velocity is represented by v1. Now, what does that mean? This graph, the yellow graph, that is basically v1. It's a straight line. How do you find straight line equations? You have the y-intercept given already. Y equals mx plus c, right? Just use that. It's a straight line to find this equation. Y equals mx plus c, right? In this case, we have velocity and time. So we could say this is v equals mt plus c, right? v1 equals mt plus c. That's what the equation is going to look like. Now, do we know the gradient of this graph already? We already found that in the first part. That's 0.02. So that means it's v1 equals 0.02 times t plus c. What's the y-intercept? It's 1. This is the equation of the first graph. v1 equals 0.02 t plus 1. Okay. Now they're asking to show v1 minus v equals this. Now you have v already. What's v? V is 0.04 t. Let me just copy this from here. This is v. We have to find v1 minus v. And basically show that v1 minus v equals this. Now let's do that. v1 minus v equals this. Let's do the subtraction. v1 minus v. What does that give you? 0.02 t plus 1 minus 0.04 t plus, or let me write like this first, 0.04 t minus 0.00005 t squared. And that simplifies to minus 0.000. No, this is going to become positive, sorry. Minus into minus, I'm writing the quadratic term first. So that's 0.00005 t squared And then the linear terms, 0.02t minus 0.04t, that will be 0.02 minus 0.04. That's minus 0.02 minus 0.02 times t plus 1. This is V1 minus V. All right. Now they're asking us to show that this actually looks like this. Okay. Now, one way to do this is that you complete the square for this, or you could also do the other way around. You could say, simplify this and prove that this basically is equal to this. So you could go either way, right? You could go either way in this. But if you want to complete the square, how would you do that? You would first take this common outside 0.00005. That leaves you with t squared minus 0.02 divided by 0.00005. That's giving me 400. So t squared minus 400t plus 1 over 0.00005. That's giving me 20,000. That's what we get when we take this common. Now we have to complete the square for the part that's inside, right? Complete the square for this. We can have the constant on the side here. Add 200 square and subtract 200 squared. Okay. What does that give us? 0.0005. That stays outside. This gives us a perfect square, t minus 200. So we have t minus 200 whole squared. And then minus 200 squared, that's minus 40,000. Just confirm, 200 squared. That's going to be 40,000. Plus 20,000. Let's simplify this. Let's simplify this and see what that gives us. 0.0005 into t minus 200 squared minus 20,000. And now we multiply this number outside inside, and you get 0.0005 into t minus 200 whole squared minus 20,000 into 0.00005. And that's giving me 1 outside, so minus 1. And that's what we had to prove. V1 minus V equals this. Now that's quite some working for 2 marks. So I would suggest you do it the other way around. Once you've gotten to this point, just simplify this and prove that these two things are equal. Okay, you can just simplify that, prove that those two things are equal. Okay, does this make sense? Any problem with this?
No, sir.
Okay, now let's look at the last part quickly. Just give me a second. Leave a message. Let's look at the last part. So read the last part and see what we have to do there. Let me just message and then we start this one. P3 threshold. Okay, let's have a look at the last part now. It says deduce that V1 minus V is between minus 1 and plus 1. Okay, now how do we think about this? V1 minus V is between minus 1 and 1. Okay, so we have already found this thing, right? So this part B, and then the last one is C. We need to deduce. So there's a reason why they've asked us to write it in this form first, V1 minus V, right? Now, once we've done this, let's see how we can prove that V1 minus V is supposed to be between minus 1 and 1. Okay, so this part is a square, and a square can never be negative. The least value it can have be 0. So let's think about it. So this is the function, right? This is the expression 0.00005 into t minus 200 squared minus 1. What's the least value that we can get for this? The least value would be when this thing is 0, right? So you can say, or actually there could be another way of thinking about this as well. Yeah, let's actually do it that way. So instead of thinking of it mentally like this, the other way to think about this could be that you say, since v1 minus v is equal to this is the quadratic expression. It's a quadratic expression which is going to be a u-shaped thing, right? Because it's t squared, and t squared is the quadratic term is positive, right? If the quadratic term is positive, the shape of this function v minus v1 minus v, that's going to be quadratic like this, u-shaped. Time is between 0 and 800. Now for time between 0 and 800, let's see how this graph looks like. What's the turning point of this graph? This is the turning point of the graph. It's completed square form. That means the horizontal coordinate of the turning point, that's 200. What about the vertical? That's -1. So it's 200 and -1. This is the turning point of this function. Okay. This is the turning point of this function. Now, if this is the turning point, what's the lowest point of this graph then? It's -1. The least value of v1 minus v is -1. What about the greatest value? The time is going from 0 to 800, right? Time is going from 0 to 800. So you have 0 on the left side. Remember, this is time. If 200 is this, point where time is equal to 0 is going to be on the right side. So maybe that's here. And point where time is 800, that's going to be on the right side. So that's here. Just find the values of v1 minus v when time is equal to 200. When time is equal to 0 and when time is equal to 800, and see what that gives you. So at time equals 0, it's like just like you used to find the range of functions in paper 1, remember? It's like that. We have to find the range of this expression, the values of the function from time equals 0 to time equals 100. The least value is -1. What about the highest value, the highest point on this graph? When time equals 0, v1 minus v, this expression gives us 0.0005 into 200 squared -1, that's giving me 1. And when time equals 800, let's see what we get from that. Or can we have 800? I'm sorry about that. We're actually only talking about the first 400 seconds, not 800 seconds. We're only talking about 400 seconds. So we don't have to check at 800. We actually have to check at 400. So the other point is going to be 400. We're just talking about the first 400 seconds, right? What about 400? Well, if you try 400 as well, it's going to give you the same value, v1 minus v. That is going to be 1. So in this interval, the lowest point of the graph is -1, and the highest point of the graph is 1. Right? So you can just show these two values, that when time equals 200, the value of this expression is -1. When time equals 0, the value of this expression is 1. And when the value is 400, when time equals 400, the value of this expression is 1. That means what's the lowest point? What's the least value of v1 minus v1? The least value is -1. And what's the greatest value of v1 minus v? The greatest value is +1. So that means v1 minus v, that is supposed to be between -1 and +1. Does that make sense to everyone? Is that okay?
Yes, sir.
Any questions on this? Any problems with this, anyone? This was a quite complicated one, especially the last part, I think. B was okay. In the last part where we had to find the range of this function, think about finding the range of this function. That was slightly more complicated. Okay, I hope that makes sense. Now, if you understand basic Newton's second law of motion, F equals ma, I would recommend that you start doing the rest of the questions from the 2 worksheets, friction and kinematics worksheet as well. I'll assign those questions so you can have a head start for the next class. In the next class, we will cover some basics of Newton's second law of motion and start doing practice questions. That's a small topic in terms of concepts, so we will just be focusing on practice questions primarily. We will do questions on Tuesday and also on Wednesday. In both those sessions, we will be doing practice questions on Newton's second law of motion. And then either Friday or Saturday, we could start work, energy, and power as well, because now I told you earlier, the remaining 3 topics are actually quite short. It's more about practice as compared to concepts. Concepts are going to be covered in like 3-4 sessions at max. We will spend the rest of the time on doing as much practice as we can. All right, that's it for today. I'll see you again in the next class. In office. Bye.